Hello viewers, welcome to add-on. In this question we are asked to write the diode current equation with their notations and meaning. Okay, so at first we need to know what is a diode current equation. The diode current equation expresses the relationship between the current which is flowing through the diode as a function of the voltage applies across it. So for example, we are considering I, this is the current which is flowing to the diode, or we can say this is the diode current. And V, this V is the voltage which is applied to the diode. This V is the voltage which is applied to the diode. So now, before remembering the equation of the diode current, one thing that we need to know that the VI characteristics of the PN junction diode, okay, the VI characteristics of the PN junction diode is like what? This is like exponential curve. Okay. So the exponential curve meaning this is like this. Okay. So as we can see, this is an exponential curve. So the relationship will also be exponential. So the diode current equation will be written as I is equal to I naught e to the power QV divided by eta of KT minus 1. Okay. This is the diode current equation where I is the diode current which is flowing to the diode. I naught, this is I naught, this is the dark saturation current. Okay. This is the dark saturation current. Okay. Dark saturation current. Okay. So what is the dark saturation current? I'm going to explain it later. First, I'm going to describe all the notation which we have used in this equation. So Q is the charge of electron. Okay. And as I have said, V is the voltage which is applied to the diode. Eta, this is the ideality factor. Eta is the ideality factor. K is the Boltzmann constant which has a value of 1.38 into 10 to the power minus 23 Joule Kelvin inverse. Okay. And T is the absolute temperature in Kelvin. Okay. So these are all the notations that we have used in the diode current equation. And one thing we need to notice that this diode current equation specifically focuses on two critical parameters. One is the I naught, which is the dark saturation current, and another is the eta, which is the ideality factor. Now, what is the dark saturation current? This dark saturation current indicates the leakage current density flowing through the diode in the absence of light. So, this is the current, or we can say I naught, this is the current which is flowing through the diode in the absence of light. Hence, it is known as dark saturation current. This parameter is the characteristics of the diode under consideration and indicates the amount of the recombination which occurs within it. Or we basically in a PN junction, the PN junction can be forward biased or it can be reverse biased. So in the forward bias, electrons generally move from the N side to the P side, and for that reason, current flows to the diode. But during the reverse bias, when the PN junction is reverse biased, the depletion region increases by a large amount of space. As a result, electrons and holes cannot cross the junction. So during that time, a little amount of current will flow through the diode. We cannot say no current will flow through the diode. A little amount of current will flow through the diode, and that current is known as reverse saturation current or recombination current, which generally arises due to the recombination of the electrons and holes. So for that reason, this is the curve for the forward bias PN junction. And for the reverse bias PN junction, the characteristics will go on like this. Okay. And after attaining a particular voltage, the diode will break. And for that reason, for example, this is the breakdown voltage minus 5 volt. So after attaining this voltage, the diode will break. And after that point, the current will just increases exponentially. Okay. So the next factor, eta, this, and one thing we need to know, this I naught will increases with a high recombination rate, and it varies directly with the temperature and inverse, and basically it varies directly with the temperature and inversely varies with the material quality. And the eta, this is the ideality factor, which indicates the ideality of the diode. As as we can say, for an ideal diode, if we consider that the diode is ideal, then this ideality factor, it will be equal to 1 in case of ideal diode. Okay. So if we consider a germanium diode, ideality factor will be equal to 1. But if we consider a silicon diode, ideality factor will be equal to 2. Okay. So depending on the question, suppose in an example, we are asked about the diode current equation for germanium. Then we will put the value of eta equal to 1. But if we are asked about the silicon semiconductor, then the ideality factor will be equal to 2. Okay. However, its exact value for the given diode depends upon various factors like electron drift, diffusion, carrier recombination, which occurs within the depletion region. Okay. And additionally, this ideality factor typically ranges from 1 to 2, fluctuating based on the current and voltage level. Okay. So, in the forward bias condition, there will be a large amount of current flowing through the diode, as I have said, because the width of the depletion region decreases. So, during this time, this particular equation will become I is equal to I naught e to the power qv divided by eta of kt. We are getting a direct exponential equation because the current is increasing exponentially during forward bias, right? And if the diode becomes reverse bias, then we have I is equal to minus I naught. Because as I have said, let me denote it by this. This portion is the forward bias portion. And this is the reverse bias portion. During the forward bias portion, the current is increasing exponentially, right? So we are getting a exponential relation, direct exponential relation here. This is the forward bias relation. Okay, because the current is increasing exponentially. But as I have said, during the reverse bias, the depletion region width increases, so electrons and holes cannot pass the junction. But due to recombination, a small amount of current, we can see here, a very small amount of current will be flowing through the diode, which is the reverse saturation current or dark saturation current or back current, we can say it anything. So this is denoted by I naught. So during the reverse bias, the only current we are getting is I naught. And as we are getting this current in the reverse direction, as we can see. So if we consider this is positive y and this is positive x-axis, we are getting the current in the reverse direction, in the negative x-axis. So for this reason, we are using the minus sign here. So this is the current equation for reverse bias, which is nothing but the reverse saturation current. And here, along with the reverse saturation current, there is an exponential increase of current. So to denote that factor, we are using a term which is related with e to the power something. Okay. Now, if the diode is operating in a room temperature, if we consider the diode is operating in a room temperature, okay. So let me just shift it. So if the diode is operating at the room temperature, we will be considering T is equal to 300 Kelvin. Okay. T is equal to 300 Kelvin. And one thing that we need to notice that this is the forward bias condition and this is the reverse bias condition. And if we just add these two, we will get the entire diode equation. So if we say this is IF, which is I forward bias current equation, and this is IR, this is reverse bias current equation. So then total current will be IF plus IR, which will be equal to this. Okay, this will be equal to this. So if we consider T is equal to 300 Kelvin and Q is equal to, this is the charge of electron, which is 1.6 into 10 to the power minus 19 coulomb, then this factor QV divided by eta kt, we will be putting the value of Q and the value of T, and value of K, as I have said here, 1.8 into 10 to the power 23 joule Kelvin inverse. Okay. So if we put those value, then I will be equal to I naught e to the power V divided by 0.025 into eta. Okay. So this will be the value of the current. Okay. And then if we are asked about the current flowing to the diode, we will be given a particular diode, as I have said. For silicon, this is 1. For silicon, this is 2. For germanium, it is 1. So if we are assuming the germanium diode, we will put eta is equal to 1 here. and voltage, we will be given a particular value of voltage. Okay, we will be given a particular value of voltage. So suppose this will be given upon 25 millivolt. So we will put this value here, and we will be also be given a value of I naught, which is in some range of 0.03 milliamps. So if you just put these values in the equation, we will be getting the entire current flowing through the diode. Okay. So this is all about diode current equation. Thank you.